recording. Let me take you to practice quiz. And there's only one question, practice quiz today, and it's a really simple one. Graph y equals x squared. Okay, 30 seconds more. All right, we had gone over this before as one of our basic functions, and the graph of it turns out to be an upward parabola. And this is an example of a polynomial function, and there's lots of aspects of parabolas and other polynomials that we're going to be going over today, so we'll generalize some things, like you may have remembered this or not. There's a number in front of this, a 1, and it's positive because anything is itself times 1. And if that coefficient in front of the x squared is positive, it's an upward parabola. If it's negative, it's a downward parabola. And we have this point over here called x-intercept, where it hits the x-axis, etc. We're going to go into a lot of details about polynomial functions today, power functions and polynomial functions. But it's kind of a long section, so it's a very short practice quiz today. And are there questions on homework or any other questions? Okay, if there's no questions on homework. Now there was an issue, there was a quiz, an online quiz that seems to have a wrong answer for the exponential functions. How many were having that issue? A couple people emailed it about that. I think it was Addison was one, and somebody else earlier emailed me about that. Anybody else come across that same issue? I think it was Max. Okay. I will look into that one if it's giving wrong answers regularly, and what I can do is just add 2 points, because I think each problem was worth 2 points each. I can add 2 points to people's score if there's one that's wrong. So I didn't make up that quiz, and I've been having a little bit of a technical difficulty getting into the how it's programmed. But worst case scenarios, I can resolve this by just adding a couple points to everybody's quiz scores. All right, if there's no questions on homework, then we are going to jump into this section. Power functions, polynomial functions. I want to check with the groups first. And so jump into your group number and say hi. Group leader, make sure spokesman of the day knows who they are. And let's just get a count off on each group. Group 1, how many of you are there here today? Group 2? Group 3, how many of you are here today? Group 4.
There's 2 of us here.
2 of you here in group 4. Group 5, how many of you are here?
There's 3 of us.
And group 6.
There's 2 of us.
2 of you. Okay, anybody here in groups 1 through 3?
Oh wait, sorry, never mind. There's 3 of us here.
3 of you? Yep.
There's 2 of us in group 2.
2 in group 2. Anybody?
There's also 3 of us in group 4. He just joined.
Okay, group 4, there's 3 of you. How about in groups 1 or 3? How many? Anybody in? Okay, I'm going to have the 2 people in group 2. You go ahead and join group 4. So unmute yourself from group 4 and pop in there and just say hi so they know you're a part of the group. And alright, so we'll just go with groups 4, 5, and 6 today. And alright. Number 1, modeling data. Can you use a linear function to model something like this? Years of education and annual salary. Now, notice how as the years go up, the average salary also goes up with these scattered dots. There might be some exceptions. There might be a person with very few years of education who has a lot of annual salary, and there might be somebody with a lot of years of education and very low annual salary. But basically, we could fit what we call a line of best fit through this. And we could probably model this with a linear function. And why we might want to do something like that is somebody might want to make a program that would, ask somebody, while they're in junior high, they might say, well, I plan on going to college, so I'm going to get my 12 years of education plus 4 more years of college, 16 years total of education. And the program could say, well, then you would expect to make, on average about this much money, and so on. And they could spit out some results like this if they could create a linear function to model it. All right. Now, can you use a linear function to model something like this, where you have class size and the amount of learning that takes place? Now, this situation might be more like this, where the line of best fit isn't a line. Now there's some exceptions, exceptional teacher over here, so it turns out that in this situation there may be an optimal class size. Maybe it's around 20 students or so. And if you have too few students, students actually do more poorly. They don't get enough interactions with other students. And you get packed too many students in a class, and you get too much chaos and too much time spent trying to just keep everybody on track, and not able to give individual help when needed, and so on. So that might be something that's curved, in which case, if all you had was a straight line function, could you use a linear function to model it? Well, the answer is yes over here, and the answer is no over here. You can't model this with a straight line. And suppose you had something like profits of a company over certain years, where the line of best fit dips and goes up. You would not be able to model this with a linear function either. No straight line is going to accurately model this. All right. Now, when you get something like this, we model it with straight lines. If it has one hump, we could model it probably with a parabola, like y equals x squared, but with a negative coefficient. We could figure it out. If we had something like this with two humps in it, turns out we would need a third degree. There, what? Control it here? Okay, you're going to help them? Okay, thanks. Give them whatever help they need. And, all right, so it turns out with two humps we would need a third degree polynomial to be able to model this situation. All right, so polynomial terminology. A polynomial looks like this. F of x equals 5x cubed plus 3x squared plus 1. What are not polynomials is if you have something with a negative exponent, like x to the negative 2. If you have something with a fractional, if your variable has a fractional exponent, like 1/2. And it turns out actually x to the 1/2 is the same as the square root of x, because the denominator comes out, and the numerator one stays there. And so that's the same as this, which these are not polynomial. To be polynomial functions of a single variable, you have to have whole number exponents. Sometimes we even say that this 1 is the coefficient of this term, because anything to the 0 is 1, so this has an x to the 0th term. Alright, so the degree, so on part B, we say the degree of a polynomial is the highest power of the variable. So this one has degree 3. The leading term, now this is going to be the first term you see if it's in what we call descending powers of x. If the highest power of x is the first term, next highest is the second term, that's kind of like a good ordering of this. It doesn't have to be ordered that way, but when it is, it's nice and easy to find the leading term. It's the first term. And then we say the leading coefficient is the coefficient is the number in front of the variable. And so the leading coefficient is 5. Right, any questions on basic terminology for polynomials? All right, we're going to go to end behavior. The end behavior for any function is asking what happens at the far right and far left of the graph of the function. So on this function right up here, we could say the end behavior of the graph above. We would just describe what happens on the far right. On the far right, the graph gets closer and closer to the x-axis. Another way of saying that is that the x-axis is a horizontal asymptote. And on the far left, the graph, way over here on the left, the graph is going to what height? Well, it's going to a height of negative infinity. So we describe what the heights go towards as we go super far to the left or as we go super far to the right. That's what we mean by end behavior. Okay, so let's show the end behavior of these graphs. A, y equals 3x plus 2. I would draw a quick picture. This has a y-intercept of 2, a slope of 3. So every time it goes to the, it rises 3, and goes to the right 1. Starts here, rises 3, goes to the right 1, and it keeps doing that. So, the end behavior, we would say, on the far left, it goes towards negative infinity. On the far right, the end behavior goes towards what height? Toward positive infinity. Okay. Now, when we state the end behavior of a graph, sometimes it's just good enough to do the following. We'd say the end behavior of this graph is that. And whatever happens in between, I'm not so concerned about. But on the far right, it's going infinitely far up. And on the far left, it's going infinitely far down. And this picture might be all I need to do to say the end behavior of the graph. We don't necessarily have to have everything in between if all we're asked for is the end behavior. And you don't have to put these arrows in the right spots too. If you stuck them way over here and way over here, that'd be fine. It's just that on the right it's way up and on the left it's way down. That's all we're really interested in. Okay, so let's go to the next one. Y equals negative 5x plus 1. And y equals x squared. We can do both of these. The end behavior on this one. Alright, it's got a y-intercept of 1, but its slope is negative, so it's going down. So the end behavior over here is down, and over here is up, since it had a negative slope. Positive slope is sending us to the right up, to the left down. For a parabola, the end behavior, we could draw a quick picture of it, or we could state that to the right it's up, and to the left it's down. That would be, now, the left it's also up. Because remember, the end behavior is the parabola. That was a practice quiz. Up and up. Alright. So, alright. If we had negative 3x squared, the end behavior would be, what? This is a downward parabola. So we could just say on both left and right side it's going down. And so now I've done a bunch of these, so let me have you do these last two. Do E and F, the end behavior of both of those, and just work on those for a little bit of time here. And enter your answer in your group chat. And group 6, what's the end behavior on E?
We haven't quite like all come to a consensus yet, but I kind of think that it's at the left down and at the right up for negative infinity and positive infinity.
At the right up seems pretty obvious to me, because if like the input was 100, 100 cubed would be really big. But why is the left down?
Well, the left would be down because if x, or the input, is negative, then and the exponent is odd, then the output is going to be a negative as well.
What's really important is that it's an odd power, so that if I had like negative 10 to the third, it's negative 10 times negative 10 times negative 10, 3 negatives make a big negative number, so it's going down over here. Okay, and then same group, group 6, what's the end behavior for F?
For F, the end behavior, both left and right, would be up.
Be up. And the key is the even power. When it's an even power, even if you have a negative input, like negative 100, when you raise that to an even power, all the negatives pair up and multiply together, and there's no extra negative, and you get a positive huge number on both sides. All right. So we can quickly analyze end behavior. Now these are called power functions when it's just x to a power. So that's the beginning part of the title here, power functions and polynomials. And understanding how power functions work with end behavior is the beginning of this. All right. Now it turns out there's only 4 choices of end behavior for polynomials. You're going to always have one of these 4 cases. To the right, up, to the left, down. This would be something like this. Like y equals 7x cubed. Another one would be just the same, but opposite. To the left up and to the right down. This would be like y equals negative 7x cubed. Because if that here, when x is a really large positive number, x cubed is very positive, but you're going to wind up taking the negative of it. So large positive inputs are going to give you negative outputs. But large negative numbers, this part will be negative, and it'll be a double negative, making positives over here. So those are 2. The other 2 cases, let me draw them smaller to fit them in. Look both up. Like y equals x to the fourth, or both down. Like y equals negative 6x to the fourth. Something like this. Then you're always, no matter how big or small x is, the x to the fourth is always positive, and then the output y is always negative. So you're going down really, really large. Now, every single polynomial function in behavior is one of these four. And that's it. Okay. Let's go to this next one. Approximately how large is 1 million plus 1? And enter this into your chat group, what you think the answer is. So group 4, what do you have? Approximately how large is 1 million plus 1?
We're gonna pass.
Pass? Okay. Let me go to group 5. Approximately how large is 1 million plus 1?
I would say just like it's not far bigger than 1 million, so I'm pretty close to 1 million.
So you just say 1 million?
I think so.
All right. Now, the most common answer that I've gotten in years past has been 1,000,001. But if you say 1,000,001, you're kind of ignoring this approximately, because you're giving the exact answer. Now, in situations where we give approximate answers, well, then actually that happens quite a bit. Like if you say that a certain city has a population of 1 million, and then one more person moves into that city, do you say that their population is now 1,000,001? No, because it was just an approximation before. So we would just say, 1 million plus 1 is approximately 1 million. All right. Now, when we're approximating, part B says when one number is 1 million times as large as the other, their sum, when you add them together, is approximately just the larger number. You just ignore the smaller number. If one is really, really large and one is way small compared to it, their sum is approximately the large number. All right. So, how much larger is x to the 23rd than x to the 22nd when x is 1 million? So let me have you think about this on your own for a minute. Okay, you can go ahead and enter any thoughts that you have about this into your group chat. Okay, let me ask group 6. Any ideas here?
We're pretty sure it's 1 million times larger.
Why is that?
Well, if x equals 1,000,000 and x to the 23rd is 1,000,000 times itself 23 times, and x to the 22nd is 1,000,000 times itself 22 times, then x to the 23rd is multiplied times 1,000,000 one more time.
That's right. Very good. X to the 23rd is really x to the 22nd times 1 more x. But when x is 1,000,000, that times 1 more million, this is 1,000,000 times larger. So when x gets really big, even though x to the 23rd doesn't seem much bigger than x to the 22nd, it really is. That is going to be 1,000,000 times as big as that one. And thus, when x is 1,000,000, let me go back to here. When x is 1,000,000, x raised to the 23rd plus x raised to the 22nd is approximately x raised to the 23rd. You just take the bigger number. Because one is 1,000,000 times bigger than the other, so their sum is approximately the bigger one. Okay, it's an important concept to get. All right. So, part D. What is the end behavior of that polynomial? Enter your guess into your chat group. Okay, group 4. What's the end behavior of this thing? Any ideas? And you can pass if you'd like. But you got any ideas? Group 4?
Yeah, I'm pretty sure it's right goes up and left goes down.
On the right, it goes up. And on the left, it goes down. And why is that?
I don't know. That's just what we discussed in chat.
Okay. All right. So there's two different tendencies going on here. This exponent is odd. And it has a positive leading coefficient. So its end behavior is going to tend to be with any odd one with a positive leading coefficient. We're going to tend towards this. This one, the exponent, is even. When it's even, the end behavior is both up or both down. But since this has a negative leading coefficient, it tends to be both down. It's going to be both down. All right. So this one leads us in this direction. This one leads us over in this direction. Now, which one is going to have the bigger influence? Well, we're interested in end behavior. What happens way, 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 way to the right when x is huge. So when x is a million, remember, this, x to the 23rd, is a million times bigger than this. Even though you're multiplying by -9, that coefficient looks bigger than this coefficient. That coefficient gets way outweighed by that we're going really far to the right, and x is going to be huge. And in fact, we're going to go way further to the right even than a million. We're going to go billions, trillions, zillions, way over to the right, the way end behavior. And so this term dominates, x to the 23rd. This becomes eventually inconsequential. We ignore it. And so we just, all we do to get the end behavior of the polynomial is you focus completely on the leading term. All the other terms become, they don't matter. Even if this thing had been f of x equals x to the 23rd minus 9x to the 22nd plus 17x to the 21st minus 6x to the 20th. Suppose I just kept going with huge lots of numbers for all the different powers on down to plus 3x plus 2. None of these would make any difference for the end behavior. All I would do is focus all my attention right here. Say, since it's odd with a positive coefficient, it's going to have this end behavior, and that's it. To the right it goes up, to the left it goes down. Alright, give me a little feedback. This is kind of theoretical. So go into the main text channel for everybody and say, I'm kind of confused, or this makes a lot of sense, or oh, I'm going to need to practice this a lot more. Just give me some feedback where you're at with this end behavior stuff.
Mr. Shankin?
Yes.
This is Destiny from Group 2, and there is technical difficulties in our group, but now all of Group 2 is back, so can we leave Group 4?
Okay, so we'll have
Cool.
a Group 2 as well.
Awesome. Thank you.
You bet. Okay. And all right, so go ahead and hit enter on your feedback in the main text channel. Okay, so there seems to be some basic understanding, but also some confusion and needing some more repetition. We'll give you more repetition. Alright. I think a bit confused, but starting to get it seems to capture it pretty well. So, some examples. Determine the end behavior. Let me pick, so these are from the textbook, and let me pick this one right here. So, number 21, state the end behavior. On the far left, put either up or down, and on the far right, put either up or down. And when you are typing this, you could just go L, and you could put either infinity or negative infinity. And then R, infinity or negative infinity. So there's, different ways you could do this, or you could say up or down because you don't have an infinity symbol, something like this. But, all right, so 21, let me give you a moment to think about that individually. All right, enter your answer into your group text channel for 21. Group 2, now that you're in existence, what's the end behavior on that one?
We said that, hang on, left up and then right down. So R, hang on, I keep having to flip through screens. Yeah.
On the far left, it'll be up, and on the far right, it'll be down. It'll look like this.
That's what we said, yes.
For number 21. All right, does everybody agree with this for 21? Or is there anybody who disagrees?
Oh, wait, we changed it. We say both are up.
You're going to say both are up?
Yeah.
All right. Both are up. And, all right, both are up is because this is, the leading term is even. If you just had y equals x to the fourth and that was it. When you had 10, you're going to get 10 to the fourth. If you had negative 10, you get negative 10 to the fourth, which is also positive. And so you're going to get positive numbers either way. So you're almost there. Getting them both going in the same direction is correct. But we're going to have to look also at this. There's a negative sign in front of the x to the fourth. So it's got a negative leading coefficient. So if we had negative, like a negative here, this would be negative and this would be negative, making this negative. So we would be getting, we were going in the right direction, putting them together, but it winds up being both down, down, and down. Any questions on this? All right, let's do another one. Well, actually, it's time for a break. Let's start again. At 1:30. And does anybody need to talk to me individually before I take my break?
Mr. Shankin, are you taking questions about the homework right now, or do you want us to do it after class?
Questions on the homework? You know what? We can. I asked for questions at the beginning, and I didn't get any. But yeah, we can come back from the break, and I'll take a time out and I'll do questions on the homework, and then we'll get back to where we are here with more examples of this. Okay.
Okay, because I came in a little bit late.
Okay.
And I heard somebody else talking about groups, and I'm in group 1, and there's 2 of us, I think, right now.
Oh, okay. So I will also call on group 1 then as well. Great.
Okay.
And your name is?
I'm Vanessa Baca.
Vanessa. Okay. And so when we start again at 1:30, you can ask the homework question then. Okay?
Okay, thank you.
You're welcome. Anybody else?
Bob, be careful, I pulled up your blankets on your head, and then, Ray has seen that after you. Okay, thanks. Yes. Just, hold it up and make sure it's not on there.
Right? them out, roll them out. Yeah, the one that you saw on the photo, it didn't look like All right, well, we shall start up again. And there was
Mr.
question.
Shankin,
Yes.
I have a question.
Uh-huh.
So, on the quiz that was due today,
Yes.
I just took it 3 times and I missed the same question, and I don't actually think it's my fault
Ah,
because the exponent questions, I know what the right exponent was, but it put it in and it keeps saying I got it wrong.
that's what 2 other people had emailed me about. And so I think it's a flaw in the quiz itself. And so I was discussing that a little bit at the beginning of class today.
I had computer issues.
Mm-hmm. Okay.
Mr. Shankin,
Yes.
this is Beverly. I had that same problem too, so I had to take the quiz 3 times. I eventually got it right by studying how exactly it was written in the previous ones.
What was the case? How was it written?
It wants you to put response in all caps, and then the little
Or
I don't remember what it's called for some reason right now.
it's called an underscore.
Yeah, that's what it is. It wants you to put response in all caps, underscore, and then your answer. No
right.
space between your answer and the underscore, though.
That's way too fussy. So what I'm going to do is I'll go in and I'm going to add 2 points to everybody's score, unless you already have a perfect score, and then I'll leave it alone. But you can get, I think it's 12 points. So if you had anything less than 12 points, I'll add 2 points to everybody's score.
Cool.
All right.
Thank you.
You're welcome. All right, and so there was questions on homework. So what's the question? Was it?
Hi, Mr. Shankin.
Yes.
I had a question on number 14 of 4.2 and kind of how, and number 20 of 4.2 also.
4.2, 14 and 20.
Yes.
Alright, so 14. So this is at 335. All right. A town has an initial population of 75,000. It grows at a constant rate of 2,500 per year for 5 years. So 14 is find a reasonable domain and range for the function p. All right. So t might be the initial variable. Is time, and it depends on how you define this. And for instance, if you say it's the years since we start, and then P is going to be population. Then the domain would be, it grows at a constant rate, and then you're finding the function. Let me do this part too, that models the population. If we did this, it would be as initial population of 75,000 plus it gets 2,500 times t. So that when t is 0, when we started, it would be at 75,000. When t is 1, it's had one time that it added 2,500. And when t is 2, 2 years later, it had 2,500 twice. And then the domain would be t between 0 and 5. Because it just does this for 5 years. And then the population would range from 75,000 at its beginning, and then at the end it would be 75,000 plus 2,500 times 5. Because 5 times it grew by 2,500. All right. Does that answer your question for number 14?
So what would the range be? Like P?
The range is P. Oh, yeah. I wouldn't put P. I'd put R for range. The domain is that, the range is that. Now that's one way to do it. Somebody else might put the time as the year number. So for instance, it might be had an initial population of 75,000 in the year 2000. And then it grows at this for 5 years. And then this could be between the year 2000 and 2005. And then the function becomes more complicated when you have the year number and so on. So that's why we like to do these and make it as simple as function as we can, is we like to have t being 0 when we start. So we say years since we started. And so we didn't know what year it started anyway, it's kind of natural to do that. But even if it said like this town had an initial population of 75,000 in the year 2000, you can always adjust your t and say years since we started. Okay, so that starts at year 0. All right, and then you had another question on 20, is that it?
Yes, it's kind of like the same question with dealing with the domain and range, but I was confused because it said find the reasonable domain and range for the weight of like a baby, and it like can't be all real numbers because it's
okay. Yeah, that makes sense. So let's copy this. I see why you'd have questions on this. Okay. As a function of, all right, so this one, the weight of newborn is 7.5 plus it gains 1/2 pound every month, and t is the number of months. So that's the equation that models it. And then the reasonable domain and range would be, the domain is something about the t. When is a baby no longer a baby? Maybe at 12 months, something like this. So when it's newborn, all the way to like 12 months. And it says for its first year, so it would go for 12 months. And then the range, the reasonable one is, they could have left out the word reasonable because we can figure out the precise range. W is going to go between 7.5 pounds when it's first born, and then 7.5 plus 1/2 times 12. Now we'd actually do 1/2 times 12, which is 6, and we'd add these together and we'd get 13.5. Yeah, so you'd say between 7.5 and 13.5. All right, so this turns out that the weight of a baby's growth is, they're saying that it's basically linear, and this will only be for a short time, for maybe the first year. If we kept growing at a weight growing at a linear rate, we'd get super huge. All right, does this answer your question for 20?
Yes, thank you.
You're welcome. Any other questions?
I had one more question.
Uh-huh.
On the list of homework assignments,
Yes.
there's a circles worksheet, but I can't find it anywhere in the modules.
Okay. Yeah, I announced that. I probably should have put that in the announcement too. I just stated that in class last time, that we're skipping the circles worksheet. It's in the schedule, but I took it out of all the assigned lists, in the assignments and in the modules and all that stuff. I took it out of there. All right, so don't worry about circles worksheet. Anything
Okay,
else?
thank you.
You're welcome. Any other questions? All right, then let's keep going with the end behavior. Oh, we were going to do some more examples like this. So let me insert some more space. All right, so let's go to this problem, number 22. Determine the end behavior. So for number 22, at the far left and at the far right, what's happening? Is it going up or is it going down? Is it going to positive infinity or negative infinity? Figure out your answer, enter it into your group chat. And you can discuss it briefly in your group. Okay, group 5. What do you have for that one? What's happening at the far left? Anybody from group 5? All right, let's go to group 1. What do you have happening in this at the far left?
We think that to the far left it goes up, and to the far right it goes up as well.
And why is that?
Because the exponent is even and positive.
Very good. That exponent is even. We only concern ourselves with the leading term. And it's got a positive leading coefficient, even as they both go in the same direction. And if it's a negative leading coefficient, they'd both be down over here. All right, so let's go to another one. Let's go to number 23. In your group chat, type in what you think is happening on the far left and on the far right. All right, group 6. What's happening?
We think that on the far left is going down and on the far right is going up.
Did you say up?
Yes, up on the far right.
Up on the far right. And how come it's going down on the left and up on the right?
Well, if you simplify or distribute the x squared, is it?
Yeah.
To all three terms inside the parentheses, you'll end up with 2x to the 5th as your leading term, which is an odd exponent with a positive slope.
Positive leading coefficient, very good. So then it's down on the left and up on the right. All right, I think we're starting to see a little bit of clarity here with a little bit of repetition. All right. So this is very similar to if it was any odd exponent, even if it was 2x to the 1st, or 2x to the 7th, 2x to the 9th. It's going to be down on the left, up on the right if it's a positive leading coefficient. All right. Now, the general principle here is the end behavior of a polynomial f of x is determined by the degree of f of x and the sign of the leading coefficient of f of x. Those two things determine the end behavior. That's it. And if the degree of f of x is even, then the end behavior is both up or both down. And it's both up if you have a positive leading coefficient, and it's both down if you have a negative leading coefficient. If the degree of f of x is odd, then end behavior is one up and one down. And the natural situation is up on the right, down on the left. But it gets reversed if there's a negative leading coefficient. All right, so if I'd have just read this to you at the beginning of all this, this would have explained all the rules, but you wouldn't have much intuition about it. It'd be really hard to memorize this. This is something we kind of, more so than commit to memory, is if we can really understand why these are true, we can really embrace these and get them quickly. But it might take quite a bit of repetition to get comfortable with it. Okay. And eventually we got to have the same degree of skill as if we had just memorized all this. All right, but that summarizes the ideas of end behavior for polynomials. All right, let's go. We're about to go to finding intercepts, x-intercepts, roots and zeros. But before we do this, I want you to do this. Don't look at this end behavior thing. Scroll away from it. What I want you to do is, in your group chat, summarize in your own words. Put it in your own words now, how you determine the end behavior of a polynomial. And then, so, type it up. Don't hit enter till I give you the cue. And this is in your group chat. Don't refer to anything in writing or anything, just think about it with your own words. Okay, and you can go ahead and hit enter. And if you didn't finish all the way, that's fine. Just put what you've got so far in. And then look at what other people have written, and you might want to change or modify yours a little bit. Sometimes hearing it from somebody else gives you a different perspective and might add to your insight. Okay, we're going to go to number 9, finding intercepts. All right, so x-intercepts, and it's only x-intercepts that are given these extra names. Sometimes they're called roots, sometimes they're called zeros of a polynomial. And let's take this point up here. We can write its coordinates. It's 0 over 3 up. That's the y-intercept, because it's where it hits the y-axis. And this 2 over 0 up is the x-intercept. Alright. So, what's always true about something that's always true about every x-intercept, and what's always true about every y-intercept? Think about that question for a moment. And enter your answer into your group chat. And let me ask group 6. What's always true about x-intercepts?
For x-intercepts, the y-coordinate is always 0.
Y is 0. And an x-intercept?
Oh, you mean a y-intercept?
A y-intercept? Thank you.
Yeah, the x-coordinate is always 0.
The x-coordinate is always 0. And it's interesting to think about why this is true. The x-intercept has got to be on the x-axis. And the y is really the height of the point. And so it makes sense that it's got a height of 0. The y-intercept has got to be on the y-axis, but the x-coordinate is how far left or right you had traveled. And if you're on the y-intercept, you can't travel anywhere left or right, so the x has got to be 0. Okay, so when we have functions like y equals 3x squared minus 7x plus 2, we'll find one of these intercepts if you are told to find the y-intercept. You would just set the opposite letter to 0. And then when they do that, this zeroes out these first two terms, and you get y equals 2, so then 0, 2 is the y-intercept. So we can get the other intercept, get the y-intercept by setting the x to be 0 and vice versa. Alright, now there's a question that I have that I didn't put on this, but I've just stated verbally. Can a function have more than one x-intercept? And can a function have more than one y-intercept? Discuss this briefly in your chat while I type it up. Alright, let me go to group 2. Can a function have more than one x-intercept?
Yes.
This is Beverly from group 2.
Yeah.
Yes, it can, but that would mean that the line is curved.
Very good. So
And same goes for y.
you could also have more than one y-intercept,
Yes, but the line would be curved.
but the
It
line would be curved.
Be with like a square function, cubic root. No, wait, not a cube function. A square function basically that's it, I think. And a reciprocal function?
Okay, I'm agreeing with you on the x-intercept, but on the y-intercept, I disagree. Because watch, let me change to red, and I'm going to erase this in a minute. Here it intersects one time. To intercept again, it would have to do something like this. Maybe it intercepts again. Is this a function? Remember, to be a function, it has to pass what test?
No, it is not a function, but
That's
it is a
right.
relation.
That's right. It's a relation. So, since I said it was a function, can a function have more than one y-intercept? The answer is, got to take that part out. This one is yes, it can have more than one x-intercept, but it can't have more than one y-intercept. Otherwise, it's not a function. It won't pass the vertical line test. And that's why the x-intercepts, there can be more than one of them, and that's why they have special names, roots or zeros in the polynomial. All right. Now, we're asked to find the x-intercepts of these three. So let me give you a minute on number 10. Do A, B, and C. Find the x-intercepts of each one of these. And enter your answers in your group chat. I'll call on a group in a minute. And I can hear somebody typing on their keyboard, so check to see if you're muted. All right, group 4. What's the x-intercept for A? Group 4, got anything? You can always pass.
We'll pass.
Okay. Group 6.
I haven't received any confirmation from any of my other group members, but I came up with just for A. The x-intercept is -2.
Okay, and how'd you find it?
I just set it equal to y. I set y equal to 0.
Put the y is 0.
For x.
And then you got this equation to solve for x, and you get x equals -2. Now, the format I'd like you to use for the x-intercept is I want you to give me both coordinates of the point. So, the x-intercepts for A, some people will say, oh, x equals -2, that's the x-intercept. Instead, I want to have the point -2, 0 is the x-intercept. Okay. Now, for the other ones, we do exactly the same thing. We put 0 in, we put 0 in. In this one, it goes, there are a couple ways you could do it, but one way you could do it is factor it. And then you state, well, x equals what values of x will cause these two things to multiply to be 0. Only two things can multiply to be 0 only when one of them is 0. This one is 0. That's caused by x being negative 3. X equals 3 would cause this one to be 0. So negative 3, 0, and positive 3, 0 are the two x-intercepts of this. Okay. This also is confirmed by what we know. Y equals x squared looks like a parabola, like this, but minus 9 means shift it down 9 units, and then make your parabola. And this would hit at negative 3 and at 3. Those would be the two x-intercepts of that right there. Okay. And this on C, this actually is a third degree polynomial. And we could answer stuff about its y-intercept, its end behavior, all kinds of stuff. But in this form, it's perfectly set up for solving this equation. X equals 3, x equals negative 1, x equals negative 5 are the x-coordinates of the x-intercepts. So 3, 0, negative 1, 0, negative 5, 0. Okay. Now, there's going to be a lot more homework problems asking you to find x-intercepts in general than y-intercepts. And why is that? Well, y-intercepts are really, really easy. If I was to ask to find the y-intercept, I just set the x equal to 0. And notice on A, the y-intercepts, let me put these way over here. Y-intercepts. If I set the x to be 0, the y is 6. You can just look at them and tell. On B, if I set the x to be 0, the y is negative 9. It just zeroes out that. C, you'd have to multiply some stuff together. But when it's factored out, then it takes a little longer. But other than this, y-intercepts go really, really fast because it zeroes out all the terms that contain x. All right, now there's some principles involved. The maximum number of x-intercepts of a polynomial f of x is the same as the degree of f of x. And let me show you. Suppose f of x was a polynomial like this, x squared minus 9. We just saw this. And we just saw that this had two x-intercepts, at negative 3 and at 3. Suppose this one had 3 x-intercepts. Then the function would have to go through these 3 points right here, and we couldn't and still have a parabola. It could be going something like this, but then it would have to come back down to go through this. And it would screw up its end behavior, but the most important thing is if you factored this, all the factors, each factor leads to a separate x-intercept. X equals negative 3 is an x-intercept. X equals positive 3 is an x-intercept. If it had 3 x-intercepts, it would have had to have looked like this. If this was at -3 and this was at 3 and suppose this one was at -5. If it was like this, it would have had to have looked like this. X plus 3, x minus 3, but it would have also had to have x plus 5 in there, so that -5 would cause this to become 0. And then all of a sudden, it's a third-degree polynomial. You can't have a second-degree polynomial have 3 x-intercepts. It's impossible. The maximum number of x-intercepts of a polynomial is the same as the degree of the polynomial. If it's second degree, it can have at most 2 x-intercepts. Now, why do we say maximum? Well, it doesn't have to have. Just because it's second degree doesn't mean it has 2 x-intercepts. If it's, let me get a little more space here. Insert. If y equals x plus 4 squared, that only has x equals -4 is the only x-intercept. Because it's the only thing that would cause the y to be 0. So it doesn't have to, because it's second degree, doesn't mean it has to have 2 x-intercepts. Y equals x squared looks like this. That only has 1 x-intercept. You could have no x-intercepts. Y equals x squared plus 5 has been shifted upwards. And it never hits the x-axis. This has no x-intercepts. Alright, so the maximum number of x-intercepts of a polynomial is the same as the degree of the polynomial. And then all polynomials have exactly 1 y-intercept. Why do all polynomials have exactly 1 y-intercept? Well, look at what the form of a polynomial is. It's y equals something with x's. And then, how do you find the y-intercept? You let the x be 0. And when you let the x be 0, you'll always get 1 answer. So you're always going to get 1 answer. And also, if it had more than 1 y-intercept, it wouldn't be a function. And they have to have a infinitely far to the left and infinitely far to the right end behavior, and it has to eventually cross the y-axis somewhere. So it's got to have exactly 1 y-intercept. So we're learning a lot of basic information about polynomials here. Turning points. Maximum number of turning points of a polynomial is 1 less than the degree of the polynomial. Let me show you. F of x equals x squared is this point right here, the lowest point at the bottom of a valley or highest point in the top of a hill is what we call a turning point. Because the graph was decreasing and then it changed to increasing. It turned from going downhill to uphill. That's why it's called a turning point. And now all parabolas have 1 turning point. Second degree, but 1 less turning point. Could a parabola have 2 turning points? Well, for a parabola to have 2 turning points, we would have to do something like this. That has 2 turning points, but now it's not a parabola anymore. And let me say f of x equals 7x minus 2, x minus 4, x minus 5. Let's just look at this real quick. This has x-intercepts at 2, 4, and 5. Because these all cause the y to become 0. It has x-intercepts at those. Now, the end behavior of this, if you FOILed this out, you'd see that the leading term would be 7x cubed. So, it's on the far right, since it's odd, it's going up, and the far left is going down. Now, it's third degree polynomial at most 2 turning points. One turning point way up here, and another turning point here. Could a third degree polynomial have 3 turning points? No, because if it had another turning point, it could have a 4th root. It can't. It can have at most 3 roots or 3 x-intercepts. And and again, that's the maximum number of turning points. It doesn't have to have that many turning points. If I have y equals x cubed, it looks like this. And it's always going uphill. It doesn't have any turning points. But the maximum number of turning points it could have is 2. Alright, so the homework is 5.2. We'll stop here. Any questions or comments? You all have a very good weekend. I'll add 2 points to the last quiz if you had less than a perfect score, and I'll look into how we can fix that problem for future semesters. But I think for this semester, I'll just add 2 points. And let me stop the video.
Bye. Thank you.